Okay, so this is quiz 8 review. Like I said, I'm gonna go over this. This shouldn't take a long time at all. So we can get this done with pretty quickly and then go over a couple things just from the lecture slides, important concepts to go over and whatnot. And then I guess if we have time at the end, if you guys have any additional questions, we can go over those. Or feel free to just kind of, leave early. Enjoy the rest of your night. So, let me get started here with problem 1. So for problem 1, rolling the dice, we have 2 fair 6-sided dice that are rolled together. Part A is asking us for the total number of possible outcomes. So total outcomes. Now, if you came to my session yesterday, you'd know that I went over kind of like a little trick to figure out like total number of outcomes. And that's just generally thinking of it this way. So I'm going to refer back to like flipping a coin, just because that's a really simple way of, explaining this type of problem. So if I have a coin, right, I can either have heads or tails when I flip it, right? So that's 2 possible outcomes for one flip. So 2 outcomes, 1 flip, right? Now, if I think about it, right, if I want to flip the coin twice, for example, right, then how many outcomes do I have then? I could have heads, tails, right? Tails, heads, heads, tails, tails. So that's 4 outcomes, right? So how can I figure this out without writing down all the outcomes every single time, right? So I can do kind of this little formula here, which is basically taking the number of outcomes in the original process, right? So in the first flip of the coin, I can either get heads or tails. So an original process, right? And then raise it to the power of, how many times I repeat the process. Number of times repeat, right? So if I flip this coin 3 times, right, I know I have 2 outcomes, heads or tails, on the first flip, and then since I flipped it 3 times, I repeated that process 3 times, so 2 to the 3rd is 8, right? Now, we can kind of do the same thing here with the dice, right? So how many outcomes do you have when you when you roll a dice? Just 1 roll with 1 dice, or one die, yeah. 6, right? So 1, 2, 3, 4, 5, or 6. So we have 6 outcomes on the first roll, right? Now, if we were to roll it 2 times, or essentially if we have 2 dice that we want to roll together, right, then that's essentially, rolling twice or repeating the process twice. So that's 6 to the 2, which is 36, right? Yeah, so you have to make sure it's not multiplying, you raise it to the power of, right? So if I repeated this 3 times, it would be 6 to the 3rd, right? If I repeated it 4 times, it's 6 to the 4th, and so on and so forth. And then I remember that you guys had, on the online homework, a lot of those really tough, annoying problems with the nitrogenous bases, right, ATGC. So in that case, right, you can kind of think of the same thing. So I have these 4 bases, A, T, G, C. If I'm just looking for one base, right, that's just one process, how many outcomes do I have? 4, right? So if I just have one place, right, there's one place in a sequence, in a DNA sequence or whatever, I have 4 outcomes. I can either have A in that place, T in that place, G or C, right? Now what if I have 2 places that I'm looking for in the sequence, right? That's like saying I repeated the process twice. So if I have 4 outcomes in the original process and I repeat this process twice, how many outcomes do I have if I'm looking for 2 bases? 16, right? So it's 4 outcomes in the original process raised to the power of 2, which is the number of times I repeat the process, or the number of bases I'm looking for, right? Now, oftentimes you'll see oh, it's 4 bases or something, right, that I'm looking for. So same thing, 4 to the 4th. 4 bases raised to the 4th power. I'm repeating the process 4 times, or I'm looking for 4 different bases. Each time I have 4 options of what could go in each place, right? I could either have ATGC here, ATGC there, and so on and so forth, right? Now, that's pretty much part A, right? I'm looking for the total number of possible outcomes. I have 6 outcomes when I roll the dice once, right? 1, 2, 3, 4, 5, 6. If I roll it twice, I take the number of outcomes in the original process, which is 6, raise it to the number of times I repeat the process, right? So 6 to the second goes to 36. Make sense? Cool. Now, they're asking for part B, what is the probability of rolling 1s on both dice, right? So on the first roll, I get a 1. Second roll, I get a 1. Now question, is rolling the dice an independent or a dependent process? Independent, right? Now what does independent mean, essentially? Yeah, exactly. So it doesn't have any memory of any past processes, right? So rolling the dice a second time, the results that you get are completely independent of the first roll, right? So just because I rolled a 1 on the first roll doesn't mean that, oh, I'm more likely now to roll a 1 on the second roll, for example, right? Or I'm less likely or whatever. So any subsequent rolls, any subsequent trials or repetitions of an independent process do not depend on any previous occurrences, any previous trials, right? So essentially, all of your trials, all your repetitions are completely independent of one another. The object or whatever, in this case, like whatever repetition you're doing, has no memory of previous events, right? So the dice don't know that they rolled a 1 the previous time, right? So it's completely independent, and basically there's just each trial is kind of its own thing, right? So this is often kind of an issue, I guess, when people think about, like, I guess if one were to gamble, then I guess if you roll like I don't know gambling. So let's just say there's a game and you roll 3 or whatever, right? And I guess you're on a roll and you're winning a lot of money, and you're like, okay, well I'm on a roll now, so like if I roll a 3, I'm probably gonna roll a 3 next time. That's the roll that I want to get or whatever, right? So that's not the case. Each time you roll the dice or each time you flip a coin or whatever, it's all independent. That's just it just happens. It's just a coincidence that you're on a roll now, right? It just happenstance that you're doing really well in the game. Because what happens with probability, or the way we kind of define probability, is that, for example, if you have a coin that you're flipping, heads, tails, heads, tails, heads, tails, right? You can repeat it a million times. You very well could have your first couple of outcomes, right? Your first like 10 trials be all heads. Does that mean, like, you know, it's always going to be heads, or the coin is like, I guess leaning towards heads or whatever? No, they're independent processes. It just happens that you ended up with a lot of heads in your first couple of rolls, right? But the key to probability is that over an extended amount of trials, over like an infinite amount of trials, right? That probability will approach some certain value. So we know that, the probability of flipping a coin, getting heads or tails, is 1/2, right? Well, if you roll, or if you flip the coin like 10 times and you get all 10 of them be heads, I mean, sure, that's fine. But just know that over a million trials, 2 million, infinite amount of trials, right? That probability is gonna eventually like even out. Like you're gonna get tails every now and then, right? You're gonna get a lot of tails, and eventually, the probability of getting heads is gonna be 1/2 over time, and the probability of tails is gonna be 1/2 as well over time. So It's just kind of like approaching a specific value. So getting, you know, a bunch of favorable outcomes in the beginning isn't an indication that like, I guess one outcome is perhaps one more likely than the other. So especially that's, the case especially for like if you have a uniform distribution. So yeah, with regards to rolling ones on both dice, bringing it back now. So probability of getting a 1 on the first roll is what? I have 6 outcomes, right? Now what are my favorable outcomes? Getting 1. Should be 1 out of 6, right? Exactly. And so the thing is, with independent processes, right? Probability of getting like 1 and 1, right? You multiply independent processes. You don't add them. So 1/6 times 1/6 should give you 1 over 36. And that's the same as thinking of like, flipping coins. If I flip the coin twice, right, I have heads, 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 tails, 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 heads, right? Well, you can see here's kind of this similar thing where I have, if I'm looking for the probability of getting heads, heads, right? So 2 heads in a row, like 2 ones in a row, for example, right? I just took 1/2, right, the probability of getting a heads the first time, multiplied by the probability of getting a heads the second time, which is just 1/4, right? Which is, I get 2 heads in a row once out of the 4 outcomes that I have for flipping a coin twice. So independent processes multiply. Remember that. That's very important. Independent processes multiply. And that's because, obviously, like I said, they have no memory of each other. They're completely independent. And so rolling the first time and getting a 1, there's only one favorable outcome, right? I can only get a 1 one time out of 6, right? Because there's only one side that has 1 dot on it, right? And so the second roll is independent of the first. There's still only one location on the dice that has 1 on it, right? And so I do 1/6 times 1/6 to give me 1 out of 36. And so if I write all the outcomes out, like I could have like 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, and over and over and over. I can just write out all 36 outcomes, right? But only one of these will be 2 ones, right? Only one outcome out of 36 outcomes will give me a 1 on both dice. Does that make sense? Any questions at all? And I'm seeing that my mic looks like it is once again, I don't know, like on the poor connection thing. But can you guys still hear me all right? Okay. Yeah, so if it's asking for rolling 3s, it would be the same thing, right? So if I roll 2 3s in a row, right? That's still one outcome, 1 out of 6, right? Because if I'm looking at a dice here, there's only one location on the dice that has 3 dots, right? So in that first roll, I can only get a 3 1 out of 6 times. I can either have 1, 2, 3, 4, 5, 6. Probability of rolling a 3 only happens 1 out of 6 outcomes, right? Same thing for the second dice, right? I have 1, 2, 3, 4, 5, 6. Probability of rolling a 3 is only going to happen 1 out of 6 times. Now, when you're like doing 2 events that are independent of each other, and you're trying to you find a specific probability with those 2 events, you're going to multiply your probabilities for independent processes. So the probability of rolling 2 1s, right, or 2 3s, for example, like you said, it would be 1/6 times 1/6, right? Same as with flipping a coin, right? So I know that getting heads on the first flip has a probability of 1/2. Getting heads on the second flip, because it's an independent process, is also 1/2. Now, getting heads on both flips should just be multiplying the probability of getting heads each time, right? So 1/2 times 1/2 gives me 1/4. And I can do a sanity check just by writing out all 4 outcomes here and be like, okay, well, I can get heads, 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 tails, 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 heads, right? And so those are 4 outcomes there. Only one of them has heads, heads, which is 2 heads in a row, which is what I'm looking for. Same thing for the dice, right? I can write out all 36 outcomes, but only one of them is going to be 2 1s. Only one of them is going to be 2 3s. Only one of them is going to be 2 4s, right? That's the idea there with finding probabilities of like independent processes when you're doing like more than one trial or event. Does that make sense for part B? Any other questions? And did you guys understand the whole probability approaching a specific value thing? Because that can happen, right? Like, just think of any time you flipped a coin or roll some dice, right? You can, get really lucky and be like, oh, I got like 10 or 11 heads in a row. But does that mean anything? No, because in the long run, over a long period of time, over many, many, many trials, that is going to, assuming you have a fair coin, fair dice, right? You're going to have that probability kind of even out to a specific value. So if the probability that we know of getting heads is 1/2, even if you did, 10 trials or something, you got 9 out of 10 being heads, that doesn't mean the probability is 9 out of 10. It just means that the first 10 rolls, you got 9 heads, right? Or 10 flips, you got 9 heads, right? But over time, that's going to even out to be overall 1/2. Right? So if I think about like 1/2 being like just saying that I can get heads, I guess like getting heads is my favorable outcome, so I can get heads once, right? And there's 2 outcomes total, heads or tails, right? Now if I repeat this process like, I don't know, 1,000 times, right? So if I were to multiply this by 500 over 500, right? So that would mean in 1,000 trials, relatively, it would be like 500 heads and 500 tails. Let's just assume that 1,000 is like equivalent to infinity. So like over a long period of time, over so many trials, roughly it's going to be about 50-50 for a fair coin, right? So like over many, many trials, right, that probability is going to even out and be 1/2. But yeah, that's part B. And then part C now is asking, what is the probability that the numbers rolled up add up to a total of 9? So this is pretty simple. It's just asking you, very straightforward probability, what values can you get that would add up to 9? So when I roll 2 of those dice, I can get like 1 1, 1 2, 1 3, or whatever, right? And I know there's 36 total outcomes, right? Because I know here from part A, I calculated 36 total outcomes because there's 6 outcomes in the original process of rolling a die. And then I repeated it twice, so 6 to the second is 36. So now I'm just looking for what type of rolls can I get would add up to 9. So you have 1 2 3 4 5 6 on the first die, 1 2 3 4 5 6 on the second die. So what combinations can add up to 9? Yeah, 6 and 3, right? 5 and 4, 4 and 5, yep, and 3 and 6. So we have 4 outcomes that can add up to 9, right? So that's 4 total outcomes out of 36, or 4 favorable outcomes out of 36 total outcomes, right? So that's just 1 out of 9. And that's just simplifying the fraction. And so 1 out of 9, you can either just keep it as a fraction or you can write it as 0.11111 repeating. But yeah, that's a very straightforward problem overall with the probability stuff. Just make sure to remember that when you have independent processes, when you're doing like a bunch of them together and they're asking you for a probability of getting a specific outcome, you're going to multiply the probabilities together. Yeah, I think, or at least I hope, that you guys are going to get something like this, because, I mean, this is, whatever you're learning here in 131 is just going to be kind of like intro to a lot more, like, I wouldn't say intense. I mean, it's still kind of basic probabilities, nothing like stats related, but it's just kind of an intro to what you're going to be doing in 132 anyway, so I don't think they're going to go like too crazy with this. At most, what I think they might pull, and I'll go over this at the end, is some like degrees of freedom questions just to change things up a bit from year to year, maybe. But otherwise, like, I think obviously they have to give you a pretty straightforward like probability question. So here's hoping that you can get some easy points on this, because I know I think I had a couple friends that had like a bad run of quizzes, and so this came up and it was like easy money. So hopefully that's the case for you guys as well. But if that's it for problem 1, if you guys don't have any other questions, and then are we good to move on to problem 2? Okay. So problem 2, very, very similar to written homework. Says speeds of molecules from a gas at a temperature of 350 Kelvin are measured, yielding the histogram shown to the right. For computations, you may assume that for each bin, the molecules have a speed equal to the intermediate value of the bin. So if I have, let's see here. Yeah, so, they already gave you the, my bad. They already gave you the values for each bar. So the speed here would be equal to 150. Well, that's red on red, so it doesn't look. This is 150, and this is 450 for this bar. This is 750 for this bar, and then this is 1050 for this last bar, right? So remember that written homework problem, if we're calculating like averages or whatever, these are like the values that we're going to be using as the values that we're interested in, right? So 150, 450, 750, and 1050 meters per second. But yeah, so and if they didn't give you these values, by the way, if they just happen not to, you can just kind of look at the this histogram, and this is the proper way to draw a histogram. This is what I was talking about yesterday with the homework session. So you can see here that the bars are clearly touching each other, right? And then they the only thing that they don't have here is that the range of values, in a sense. They sort of do, but they just don't have it like listed out clearly, because what you can do here is essentially figure out just using the scale. So if this is 200 here, I mean, it's going to be like 50. This is going to be 100, or yeah, 100, 150, 200, 250, 300, right? So right in the, and this is 0, obviously. So 0 to 300, right in the middle of that is the 150, right? 300 here to 600, right in the middle is going to be the 450, right? And so on and so forth. So if they don't give you these values, just like look for the middle value in between the ranges. So from 300 to 600, right in the middle is 450, right? Does that make sense? And that's if they don't give you the ranges. So just look for the value that's straight in the middle. That would be the one, if you're using histogram, that would be the one to use for your data values. Now, I was really feeling myself with this quiz because part A, they really gave us 2 points for calculating temperature. So, I mean, let's just hope that no one does any computation errors or anything like that. But this should be an easy 2 points here. So they're asking us, what is the temperature of the gas in degrees Fahrenheit? So they already gave us the temperature in Kelvin, right? So this is just a matter of converting it to Fahrenheit, right? So 350 Kelvin. And yes, I believe we do have this on the formula sheet. Let me check the formula sheet for my quiz here real quick. Yeah, they give you the conversion from Kelvin to Celsius to Kelvin, Kelvin to Celsius, same thing. And then from Fahrenheit to Celsius and Celsius to Fahrenheit. They give you both on the equation sheet. So we know that the temperature in Kelvin, right, that's going to be equal to temperature in Celsius plus 273, right? So 350 Kelvin is equal to the temperature in Celsius plus 273. And so that's going to give us the temperature in Celsius being 77 degrees Celsius, right? And so we have an equation of going from Celsius to Fahrenheit, which is the 9/5 times the temperature in Celsius plus 32 is equal to the temperature in Fahrenheit. So, yep, 9/5 times 77 plus 32 should give us the degrees in Fahrenheit, and that should be what? Yep, 170.6. degrees Fahrenheit there. So pretty simple for part A, right? Not too bad. Part B now. Oh, well, I forgot to... Okay. So let me kind of, real quick, because I forgot to just X this out, because I don't have access to like the blank quizzes. I just have like the answer keys. And so I just have to kind of like blur those out. And I forgot to do this last one. Anyway, part B is asking for the RMS speed. Once again, this is really, really similar to the written homework from last night. So they're asking for the RMS speed, right? So the RMS speed is equal to what? Do you guys remember from last night? Square root of what? Oh, is it still showing? What? Okay. Well, I mean, it doesn't matter. We're going to go over it anyway, but it's just I don't have room to like write at that point. That's weird. Okay. Thank you for that. Yeah, square root of v squared, not x squared. So we're doing RMS speed, not like position, right? Or displacement or whatever. So yeah, Kate's absolutely right. V squared, and then important notation is that the exponent should be on the inside of the brackets, right? This is a really important thing. So yeah, you just change the variable to v because we're talking about speed, right? Now if I ask for like RMS like position, it would be that same thing but with x. On the equation sheet, I think they just put like x, big X, as in like whatever value you're interested in calculating. So that could be, you know, position, that could be velocity or speed or whatever. They just have that big X as being like some value that you're interested in, because they also have that for the probability of certain values. And so remember on the written homework, they were doing speeds here where we had like 100 meters per second and whatnot, but those were speeds. And so you'd have to change this to VRMS essentially to match up with the value that you're looking for. But yeah, that's just a simple variable change. But you guys got the idea 100% correct with the exponent on the inside of the brackets. So for the RMS speed, I'll just kind of draw it all under the radical here. So what's the formula to calculate this value right here? This average speed squared with the exponent on the inside. Yep, excellent. So we're going to take the speed squared times the probability of each speed, right? So if I look at the first speed, right, they had 150 meters per second, right? That was the value that they gave us. So I'm going to square that and multiply it by its probability. So only tough work that you have to do is kind of, well, they outlined it here pretty well, but on the actual quiz it's kind of hard to see the tick marks. But essentially, this is about what? 12, 14, so 12, 10, 12, 14, 16, 18, 20. So this is 12, 14, 16. So this is about 16%. So careful, really, really be careful about this. Because they could either do just normal probability like 0.16 and 0.06 and whatever, or they could do percentages, and I'm fairly certain they're probably going to pull percentages just to trip people up and make sure that you're paying attention. But if it's a percentage and it's just like a solid number, 16, just an integer, right? Know that's 16% or 20% or whatever, and that's 0.16, right? So move over 2 decimal points to get the probability. So in this case, it'd be like 150 squared times 0.16, right? And the next value is 450 squared. And then what's the probability here? This is 42, 44, 46, 48. And then this is somewhere in between right here, right? So that's about 0.49, right? 49%, so 0.49. And then what do we have? 750 next. That's squared again, multiplied by the probability. Oops. 20, 22, 24, 26, 28. And then sort of in the middle here, so 29. About 29% or 0.29. And then we have this last one, 1050 squared. And we can look over here. So 0, 2, 4, 6. Yeah, this is about 6% here, which is 0.06. So quick sanity check when you're doing this on a quiz or an exam or whatever. If you're not too confident in your counting abilities, or if you feel like the graph was just a little bit off and you're not sure about the tick marks, go back and add up the probabilities. So do 0.16 plus 0.49 plus 0.29 plus 0.06, right? Make sure the probabilities add up to 1. If they do, then you're good, because all the probabilities should add up to 1. Big rule there to check at least that your stuff makes sense. Because like you could overestimate one of the values and underestimate another, and then they would even out and be equal to 1, and then you're okay to a certain extent, I think. Yeah, but at least like just make sure that all the probabilities add to 1 and that it's what it's supposed to be, and that makes sense. So if we calculate this out, right, what do we get? $432.55. Let me check my math, because I got a little bit off from that, or a lot of bit off from that, I think. But yeah, I got around 576. 576.3 is what I got. So I would check, make sure that you didn't mess up like a decimal point here or there or something like that. But yeah, so that should be the RMS speed for this part B. Is everyone on the same page now with regard to the calculations, or is anyone still confused? You got it now? Okay, awesome. Okay, so now we can move on to part C. Yeah, I would watch out for your for calculator mistakes as well, just because it's probably one of the most disappointing things in the world, to be honest. Making a calculator, like doing everything right, doing all the right work, and then you just mess up your calculator if you input something wrong, or I don't know, you put a square somewhere where it shouldn't be, or whatever. Like you might have squared the probability instead of one of the values. I don't know. So just watch out for calculator mistakes. Yeah, that's probably one of the worst things that you can do is have everything right and then mess up the calculator. That's just kind of disappointing. But at least you got the work right, I suppose. So that's probably more important, because then you'll get points. Like if this was worth, what is this worth? 5 points, you'll probably get like 4 out of 5 or 4.5 out of 5 for doing all the right work. You might have just messed up your answer. But yeah, so final part here is asking about the mass of an individual gas molecule in Daltons. So 1 Dalton is 1 gram per mole, right? So like 16 Daltons is 16 grams per mole. 345.87 Daltons is 345.87 grams per mole, right? So essentially we're just looking for the molar mass, right? So because if we have the molar mass, for example, is, I don't know, 150 grams per mole, right? Then we know that 1 gram per mole is 1 Dalton, so 150 grams per mole is 150 Daltons. So that's our mass in Daltons. But essentially we're going to be looking for the molar mass at least at first. So kind of similar, once again, to the written homework from last night, right? We have temperature, the 350 Kelvin. We know our RMS speed, which is 576.3 meters per second, right? And we're looking for our mass, essentially, right? So how can we relate all those values together? Temperature, mass, and speed. Any ideas of any equations we could use that would relate those two or those three variables together? Yeah, excellent. The average kinetic energy equations, right? So our average kinetic energy, one of them is 3/2. Yep, excellent. Yeah, 3/2 kBT. And then it's also equal to half mv squared, right? And this half mv squared here actually is the RMS, right? So it's just your 576.3 squared. So when we're looking for our speed here, the half mv squared, right? The v should be your RMS speed. But yeah. Anyway, basically, we're gonna just plug in our values, right, and solve for our mass. So we can just kind of multiply the half over, or the 2 over here, right, which would cancel with this 2, and then we can divide by v squared to get our mass. So mass should be equal to 3 times kBT over v squared, right? If we can multiply over the 2, it would be 2 times 3/2. 2 times 3/2, the 2's could cancel, you'd be left with a 3 kBT, and then you divide over the v squared, right? And you get your mass. So what units will the mass be in at this point, though, right? I mean, we know that Boltzmann's constant is joules over Kelvin. This is Kelvin, and this is meters per second, right? So yeah, it'll be in kilograms, right? Because everything else is in like SI units, right? So we should end up with the SI units for mass, which is just going to be kilograms. So if we do this real quick, 3 times 1.38 times 10 to the negative 23 joules per Kelvin. We had 350 Kelvin. And then our RMS speed was, what, 576.3 meters per second. And then square that, right? What should we get for our mass? And like I said, this is going to be in kilograms. Let me calculate this real quick, just to be sure. Yep. 4.36 times 10 to the negative 26 kilograms. Yep, sounds about right to me. Yep. So now that we have it in kilograms, right? Well, how can we get that to grams per mole and then to Daltons after that? Because we know that this would be the mass of an individual gas molecule, right, in kilograms. So this is 4.36 times 10 to the negative 26 kilograms per gas molecule, right? So like, think about it. Kilograms per molecule to grams per mole. Yeah, first you can multiply by 1,000 grams, right? 1 kilogram is 1,000 grams, right? That'd give you grams on the top. But how do we get to moles? Yep. Avogadro's number, right? So we know that there are 6.022 times 10 to the 23 molecules in 1 mole, right, of gas molecules. So that would give you grams per mole as a whole. That rhymes. Awesome. So, oh wait, can you hear me now? Is that better? Or should I refresh? You know what? I'll probably refresh just to be safe. Okay, is that better? Okay, cool. But yeah, yeah, if we can just go about this calculation real quick, then we get grams per mole, right? Because we have kilograms that cancel out, molecules that cancel out, and then you're left with grams here over mole, right? And so from grams per mole to Daltons, well, whatever you get in grams per mole is just going to be equal to the amount of Daltons, right? Because 1 gram per mole is 1 Dalton, so like 16 grams per mole is 16 Daltons. 345.87 grams per mole is 345.87 Daltons, right? So whatever answer we get here is just the same in Daltons. Anybody got an answer for the grams per mole yet? Yeah. Yep. Sounds about right. 26.2 Daltons. I got around like, because I think I didn't round at first. And so I got around like 26.32 Daltons, but all the work's right. So, because that's going to be 26.32 grams per mole. So, like I said, 16 grams per mole is 16 Daltons, 15 grams per mole is 15 Daltons. So, 26.32 grams per mole should be 26.32 Daltons, or, my bad, this is, well, phenomenal. So I'll say like 26.32 Daltons, right? Whatever, 26.2, 26.3, all the same. But that's problem 2 as well. So that kind of sums up the quiz problems here that we have. Any questions at all about any of the parts, or anything you want to clarify before we move on to like a couple things that I suggest to kind of like look over a bit more? Yeah, so VRMS and XRMS, they're basically going to be the same thing, same calculation method. It's just that VRMS is for speed and XRMS is like for position. Right? So like, I guess, I mean, I don't want to move on to the slide just yet. But yeah, I mean, the way they have it on the formula sheet is like a large X, like a uppercase X, right? And that just notes or denotes like whatever value you're looking for. So like that's just a variable that you can throw in, right? So if I just put V, because that V is like velocity or like speed, right? If I'm looking for the RMS speed, then that's what I'm going to go for. I just put V there, right? But it's all the same. It's just a matter of like what value you're looking for. So I'm looking for the RMS like distance, right? Because like with the random walk, you remember that problem that we did on the written homework where it was like right, left, and left, right, and whatever with the coins. So that would be like your XRMS because that's like the distance away. This is speed, right? So VRMS. So it just kind of depends on what value you're looking for. But the calculations are the exact same. Yep. And they all follow this formula here. So like if I'm doing speed, it would be like my speed squared times my probability of each speed. If I'm doing my position or like my distance, it would be my distance squared times my probability, right, of each distance. And that's specifically for like V's, or like the average speed squared when the exponent is within the brackets, right? Now if the exponent was outside of the brackets, so it'd be like this or this, right? That would just mean I'd be doing like my normal average, right? I just take my speed times my probability and then add up all those values, right? So I'd like do this whole process just without squaring any of my speed values. So I just take out all of these squares, right? And then at the very end, whatever average speed that I get, I'm going to square that, right? So if my average speed is like 10 meters per second, I square it and I get 100 meters per second, right? Or in that case, like that would be more like 100 meters squared over a second squared or whatever, but you know, you get the idea. So same thing for a position, right? For distance. So I have like my distance or my position times the probability of each one, right? And then whatever answer I get at the end, at the very, very end, I take it, my average distance, and I square that. So my average distance is like 3 meters away. I square it, I get 9 meters away, right? So it'd be like saying I did this whole entire process here, not including the square root, by the way, just the interior here, which is just this, right? I'd be like, if this was like 150 meters, 450 meters, 750 meters, I'd remove all the exponents, do 150 times 0.16, 450 times 0.49, 750 times 0.29, add them all up, say I get like 400 meters per second or something, right? I'm just making stuff up. Then I would square the 400 at the very end to get this value, right? So you can see here, for example, like if I were to do, let me do that real quick. So if I were to do this value over here, that would just be doing like 150 times 0.16, right? So I can just do 150 times 0.16 plus, what's that, 450 times 0.49 plus 750 times 0.29 plus 1050 times 0.06, right? So if I were to do that, 150 times 0.16 plus 450 times 0.49 plus 750 times 0.29 plus 1050 times 0.06, right? I'm going to get like 525 meters per second for this, right? Now, then I would square that. 525 squared would get me like 275,625 for my average speed squared with the exponent on the outside. Now, if the exponent was on the inside, it would just be this here, 150 squared times probability, 450 squared times the probability, and so on and so forth. So that's the difference between, that's one of the things I was going to say, like, for you guys to focus on is like the difference between like the speed or the distance squared, whether the exponent is in within the brackets or outside the brackets. So if it's outside of the brackets, you figure out your average normally using this equation, and then you square your average at the end, right? So like I said, I got 500, I got 525, I square that at the end and I get a bigger answer, right? Now if I'm doing the v squared with the exponent within the brackets, right, when it's inside the brackets, I do this equation here, right? I take every speed or every position, I square it first, then multiply the probability. So 150 squared times the probability, 450 squared times the probability, 750 squared times the probability. Add all those up, and that's my speed squared when the exponent is in the, or is within the brackets, not outside. So does that make sense? But yeah. Any other questions about any of these problems? Oops. Because if not, we can probably just move on to the slides real quick to go over some important concepts. We all good? Okay. All right. Let's see here. Thermal energy. I don't know if there's much that you necessarily need to know, or I think that you need to know for the quiz about thermal energy, but just general definitions and different like relationships and stuff between thermal energy and temperature. So if something's hotter, right, it has more thermal energy, so an increase in temperature will increase the thermal energy, decrease in temperature decreases the thermal energy. That's kind of a important thing to know about thermal energy. It's random motion of microscopic pieces of objects. This is just more or less kind of like a definition page. Okay, so forces creating thermal energy. So like friction is what we call a dissipative force, right? So it'll create thermal energy in a way, right? So imagine like if you're just kind of like, I guess, if you know like how you get like carpet burn sometimes, so that's like thermal energy kind of generated as well, because that's friction between you and the carpet. So friction is a dissipative force because it'll do negative work, right? And that negative work is not able to be stored as potential energy, and it'll just go into thermal. So your thermal energy is just the work from friction most of the case, most of the time. So I remember that one problem that we had on the practice exam not too long ago, the second practice exam, where they had like the hill or whatever, and it had like a rough patch at the end there. That rough patch had like some coefficient of friction, right? So when the block rolled past it or slid past it, right, it generated some thermal energy in that case. So they have here listed like two perspectives of how to think about dissipative forces like friction. You'd either think about them outside the system, so they do negative work on the system, or they could be inside, so they increase the system's thermal energy. I don't think you have to worry too much about like the two perspectives or whatever. Just know that thermal energy is basically equal to the work done a lot of times just by friction, right? So like it'd be FD cosine theta, right? And oftentimes it's opposite, right? So cosine 180 is just negative 1, right? So it's just opposite to like the intended motion. So if I'm moving to the right, friction is moving to the left or opposing my motion, right? So the work done is going to be negative. And so I'd have like force of friction, so it would be like kinetic friction, for example, times the distance, right, FD, and then the absolute value of that is equal to the thermal energy. But yeah, I don't think this made up like the chunk. Not even on the exam did you really have to like do a whole bunch with thermal energy. But yeah, I would kind of like briefly just go over some of these problems as well, just to kind of refresh your memory. This is where it gets a little bit more important. So temperature, this is more like chemistry stuff. So higher temperature objects move at a higher speed, so higher temperature, higher speed, generally, right? And that's because we define temperature as kind of like the average kinetic energy, right? So temperature of an object, how much energy the individual atoms have on average, right? Hotter things have more energetic atoms, so that kind of goes back to like the average kinetic energy is 3/2 kBt, which is also equal to like the half, well, I ran out of space, half mv squared, right? So higher temperature, since those two are equal, half mv squared and 3/2 kBt, right? So higher temperature, like higher speed, right? Higher speed, higher temperature, kind of related. So, and we define temperature as the average kinetic energy as well. And the reason for that is, I mean, if you look at 3/2 kBt, right? Well, this part is essentially constant, so the only thing that's kind of dependent in that case is temperature. So we kind of define temperature as the average kinetic energy. So if your thermal energy is total energy of the atoms that make up an object. So for thermal energy, there goes into it kinetic energy of just the molecules like bouncing around, colliding, and whatever. And then their interactions between the molecules, which is just potential energy. Once again, this is more like definition-related stuff. I don't think they're going to ask you like a question or have a problem that's directly asking any of these definition things. This is temperature scales. Just, you don't have to know the or memorize the temperature scales or temperature conversions. They're all going to be on the equation sheet. But just know that you can convert Kelvin to Celsius, Celsius to Kelvin, and then from that you can convert Celsius to Fahrenheit, Fahrenheit to Celsius, and whatnot. This is the conversion rate for Celsius to Kelvin, Kelvin to Celsius. Absolute zero, all the energy is at a minimum, right? So if you have, for example, an ideal gas, there's not much interaction between like the molecules of gas, so you don't really have potential energy, so it's mostly just kinetic. So if absolute zero is the the temperature at which energy is minimum, if you only have kinetic energy, right, for an ideal gas, then at absolute zero, your kinetic energy would be zero because it's the coldest possible temperature when the energy is at a minimum. Energy is at a minimum when energy is zero, obviously. So that's the lowest energy that you can have. You can have negative energy, right? So when you have 0 joules of kinetic energy for an ideal gas, you're at absolute zero, right? And just think about absolute zero being like so cold that literally nothing can move, right? But yeah. This degrees of freedom stuff, I don't think they really went too in depth with it just because this is something that you're going to be doing for like the first 4 weeks of Physics 2. So I wouldn't worry too much about it. Just generally know that like basically degrees of freedom is more or less kind of like the just the ability of a particle to kind of have like freedom of motion or whatever, like in different directions. So like if you have a particle that it could probably move like in X, Y, and Z directions depending on what type of particle or molecule it is, right? So if I have, you'll learn about this in Physics 2, but just a jet, like one regular particle just like that can move in the X, Y, or Z direction or whatever, right? So there's 3 like degrees of freedom in that case for that particle because it can move in those 3 directions. They have an example here of like a block on a spring. So you have 2 degrees of freedom. So 2 ways, essentially. Degrees of freedom are ways that you can store energy, essentially. So in terms of like the velocities, right? So I can have like my kinetic energy be stored in either in the X, Y, or Z directions, essentially. For potential energy, right? For a block on a spring, that could be stored essentially with the with how far the spring stretches. And then I can also store like kinetic energy because like if you stretch a spring, for example, and then let it go, it's obviously going to move and return back to its original position, right? So there's some velocity there. So you have energy that can be stored either in the X direction, right? That's kinetic energy where it's just moving, or you can have potential energy stored in like the stretch of the spring, right? So yeah, degrees of freedom is, I don't think you have to worry too much about that. This is the equation for average energy per degree of freedom, right? So in 1 degree of freedom, your energy should be half kBT. Now, for your average ideal gas, right, you have 3 degrees of freedom, like we said, Vx, Vy, and Vz, right? So your average energy for an ideal gas, right, should be 3/2 kBT, right? Because we have 3 degrees of freedom, right? This is your average energy for an ideal gas. Now, if they're looking for the total energy, that's different. That's with total degrees of freedom, right? So this is like, we know that one particle has, let's say one particle or one like molecule of an ideal gas has 3 degrees of freedom, right? So how many degrees of freedom would like 1 million particles have? Three million, yeah, right, exactly. So if I have each particle or each molecule of an ideal gas having 3 degrees of freedom, if I have 1 million molecules or 1 million particles, right, there's a total of 3 million degrees of freedom. So this is another important concept, which is, I have 3 degrees of freedom here, Vx, Vy, Vz. So if I have, Avogadro's number of molecules, right, 6.022 times 10 to the 23 molecules or particles or whatever, I would have a total of Avogadro's number times 3 degrees of freedom. That would give me my total thermal energy, which is this equation right here. So this F is not the degrees of freedom in one particle, which is 3. It would be the total degrees of freedom. So the total thermal energy would be like 3 times the number of molecules. So 3 times molecules. But my average energy, that would be 3/2 kBt. Because it'd just be like for one particle. Does that make sense? Any questions about that at all? Nope. Okay. Okay, this is just going over Avogadro's number in moles again. This was the two important equations that we have for average kinetic energy, which you guys seem to be really familiar with, which is awesome. You have half mv squared, 3/2 kBt, right? And then what they mention here, I think on this slide or maybe the next one, but this v right here, you see that? That's the v squared with the exponent on the inside. You see that? So that's the vi squared times the probability from earlier. Remember that? So we should be plugging in right here our RMS speed. So if we go back to if we go back to the quiz here, remember we got our RMS speed and we plugged it in to v here and we squared that. And the reason why is if you think about it, right, we have VRMS as being the square root of this, right? So how do we just get v squared alone? Well, if we square VRMS, if we take that squared, right, then that gives us this, right? Because we can just, if we square this whole thing, square this, right, we get rid of the square root, and so you're left with this value right here. So if we take the RMS speed and square it, we'd be getting this value on the inside. So when you're doing your calculation using half mv squared, use your RMS speed and square it. You see what I mean? Does that make sense? So the v that you're using here should be your RMS speed. So if my RMS speed was the 576.83 from before, I do half times m times 576.83 squared. But yeah, this is a really good example problem just to kind of differentiate between all the different terms and stuff. So total thermal energy, remember, we were saying that, okay, if each particle is 3 degrees of freedom, right, then we have to multiply by the number of molecules to get the total thermal energy. So we know that's, the equation for it is F over 2 times kBt, right? So I know there's 3 degrees of freedom per molecule. I have 1 mole of particles, right? So times 6.022 times 10 to the 23. That'll give me a total of, around 18 times 10 to the 23rd. Degrees of freedom, right? And so then I multiply that by kBt divided by 2 to get my total thermal energy. If I did my average kinetic energy, right, per particle, well, I know that each particle has 3 degrees of freedom, right? So it'd be 3/2 kBt that I'm looking for. Because remember, here they said the average energy per degree of freedom, but what they're asking for here is the average kinetic energy per particle, right? Well, I know a particle has 3 degrees of freedom, so therefore this should be 3/2 kBt, not 1/2 kBt. 1/2 kBt would give you the average energy per degree of freedom, but I know in one particle there's 3 degrees of freedom, so the average kinetic energy per particle should be 3/2 kBt. This part right here with the whole like 3/2 and 1/2, is that what you're asking about? Yeah, so before they were saying that the average energy per degree of freedom is 1/2 kBt, right? So in 1 degree of freedom, if I have 1 degree of freedom, right, then my average energy should be equal to this, 1/2 kBt, right? So let's say, for example, there was a particle. This particle can only move in like the x direction, for example, right? So it only has 1 degree of freedom. So if I'm trying to figure out the average energy per degree of freedom, then it would be 1/2 kBt. This one here, whatever like your numerator here is, that's going to be where your degrees of freedom are located. So if I'm looking just for 1 degree of freedom, or like per degree of freedom, right, then this is the equation I'm going to use. So this is my average energy for 1 degree of freedom. Now, if I'm looking for a particle with 3 degrees of freedom, right, so the average energy of a particle, since a particle has 3 degrees of freedom, we know that, right? That can move in Vx, Vy, and Vz. So the average energy in that case would equal 3/2 kBt, right? Because in this case, I'm looking for the average kinetic energy of a whole particle, right? This is just the average energy per degree of freedom. So if I multiply this by 3 degrees of freedom, right, well, that'll give me the average kinetic energy of a particle, because we know a particle has 3 degrees of freedom. So this is just saying like the average kinetic energy for 1 degree of freedom. So if I have 3 of them, would be 3 times this, right? So the distinction here is per degree of freedom versus per particle. I know that a particle has 3 degrees of freedom, right? And I know that the average kinetic energy per degree of freedom is 1/2 kBt, right? So if this is per degree of freedom, well, if I have 3 degrees of freedom, then 3/2 kBt is the average energy per particle in that case, because one particle is 3 degrees of freedom. So the distinction here comes per particle versus per degree of freedom. So average energy in 1 degree of freedom is 1/2 kBt, and 3 of them is 3/2 kBt. And it just so happens that in an ideal gas, there's 3 degrees of freedom, so that the average kinetic energy in one particle is 3/2 kBt. So it's always 3 when we're talking about like an ideal gas particle. It differs, and this, once again, this is just 132 stuff at this point, but it'll differ for like a liquid or some other substance. But for now, it's just going to be 3 when we're talking about a particle. Particle of an ideal gas will be 3. That makes sense, Kate? Yeah, for C. So they're asking what speed does this correspond to, right? What's the RMS speed? So if I figured out my average kinetic energy per particle of gas, right, which is the 3/2 kBt, that's the average kinetic energy that I got. So I set that equal to half mv squared. So what I did was I essentially broke this stuff into 2 steps. So I figured out what 3/2 kBt was in part B, and then I set that equal to half mv squared and solved for v. Does that make sense? Because if they ask for average kinetic energy per particle of gas, right, I figured out the 3/2 kBt, and I got 6.2 times 10 to the negative 21 joules, and then I set that equal to half mv squared to figure out my speed, my RMS speed. Does that make sense? Or is that still unclear? And Kate, does that make sense too? Like both for B and C overall? Okay, awesome. And to not get confused, because they had K here and they had E here, right? So, the E here obviously is just denoting just a general like energy and overall. But when you have an ideal gas, there's really not like potential energy all that much because the particles are just moving a bunch all over the place, right? So we just consider like kinetic energy. So we're just talking about energy with an ideal gas. We're just talking about kinetic energy. So that's why I could use 3/2 kBt, and then I'm kind of set that equal to half mv squared, which is I just basically used this equation. They just broke it up into two parts. And then if it says for part D, if you double the temperature with the speed of the particles double as well. So I know that my V equals √3 kBt over m, right? Remember this was on the written homework as well. And so if I doubled the temperature right here, if I did 2T instead, it wouldn't double. I'd be multiplying the speed by a factor of √2, right? Because if the 2 is underneath the radical, you can pull it out and write it as √2. But yeah. Does that make sense? And I got this equation, V equals √3 kBt over m. What did I use for m in part C? It was... I don't remember. Oh yeah, here, I got it here. So I think they had the particle mass is 16 grams per mole over here. And so they only had 1 mole of particles, so it'd just be like 16 grams, I think. I believe so. Let me check that real quick. No, that's not it. They were looking for mass per particle. My bad. So we know 16 grams per mole, and we can multiply or divide that by Avogadro's number to get the grams per particle. So the mass here should be per particle, because we were looking for the average kinetic energy per particle here. So when we're looking for speed, we're looking for the speed of like each particle essentially. So if I had this as being 16 grams per mole, right? I know that 1 mole is Avogadro's number of particles, right? So if I divide that, 16 divided by 6.022 times 10 to the 23rd, right? I should get like 2.67 times 10 to the negative 23, grams per particle, right? And so if I plug that into the equation, then I think I should get the velocity that I had here, the speed that I had here. So yeah, let me check it real quick. Or not. I don't know why I'm getting a different answer. Maybe I messed this up when I was writing it. I don't know. But yeah, I got 21.55. So maybe I just wrote this wrong when I was doing it. Yeah, I got 21.6, I believe. So maybe I just wrote this down wrong when I was taking my notes. But yeah, it should be grams per particle, and then you plug that in to the equation. But yeah. And Kate, did you understand now the root 2 thing right here? Because if you have the 2 underneath the radical, it'd just be saying like root 3 kb 2t over m. So this is saying like root 3 kb t over m times root 2. And since you can multiply radicals together, right, this would just be the same thing as 3 kb 2t over m. So it's like you multiplied this part right here, which is v equals root 3 kbt over m, by a factor of root 2. Yeah. But yeah. So that's it, I think, for those test problems. And go back as well, and like if you have Dr. De Jong, I believe he has videos and he goes over these. I don't know if he went over them in class, but I know in like the optional video lectures he goes over those. But yeah. Other than that, we get into probability. We did a lot of that probability anyway, and I think you guys are pretty familiar with it so far. Just know that probabilities add up to 1, right? Remember when I was talking about the sanity check, if you add up all your probabilities, they should add up to 1. Probability of 1 definitely happened. Probability 0 will not happen. Probability of 1/2 equally likely to occur. So if you flip a coin, for example, probability of getting heads is 1/2. Probability of getting tails is 1/2, right? So 50-50. For a dice, each outcome is 1/6, right? And then this is the idea that I was talking about earlier, where if you flip a coin like millions of times, right, you'd expect that roughly half of the time you would come up with heads and roughly half of the time you come up with tails. So you can, get a bunch of heads in the beginning, but over time, that'll roughly even out to half heads and half tails. And then this is more like I guess it's kind of like a calculus representation of this, where as you approach a lot of outcomes, right, total outcomes, or total number of times the experiment is run. NZ is the number of outcomes that are favorable that you're looking for. So if I run a bunch of experiments of flipping a coin, right, roughly over time, I will get a probability of 1/2 for getting heads or getting tails. Probability distributions. So for like, flipping a fair coin, for example, your probability distribution should look something like this. So, or rolling a dice, for example, right? So you have probability on the y-axis, your outcomes on the x-axis, right? And since each outcome is the same, probability, right? Rolling a 1 or rolling a 2 or rolling a 3 is each 1/6. They would all have the same like height. And then if you think about it, since you have 6 outcomes, right? If you multiply that by 1/6, 1/6 times 6, you get a total of 1 as your probability overall, which makes sense because we want everything to add up to 1, right? And so the area underneath the curve, or area underneath like the graph, should be 1 in any probability distribution. But it just so happens that in a uniform distribution, since they all have the same probability, each outcome has the same probability, right? Then if you just take the area of this rectangle here, 6 times 1/6, then you're gonna get the probability being 1, and that's pretty easy. However, if you have like a bell curve, that's a little bit more difficult. But this is just probabilities of like the basis again. Remember that rule that I taught you guys. So like, you take your number of outcomes in the original process, right? Raise it to the power of how many repetitions, right? So if I have 4 of these bases, right, I have 4 outcomes in the first like trial, right? So if I say, for example, they're looking for 2 bases, right? So I can have ATGC in my first slot and ATGC in my second slot, right? So if I have 4 possible outcomes in the first slot and I have 2 slots that I'm looking for, it'd be 4 to the second, which is 16. If I have 4 slots that I'm looking for, or 4 repetitions or 4 trials that I'm running, it'd be 4 to the 4th, right? So that's 256. So yeah, and I would go over some of these quick checks as well. They're pretty good to kind of review things. I don't think, at least I hope, that they don't pull any of these base problems, because it's a little, unless you don't have like a stats background, or unless you do have a stats background, I think you would have a tough time doing this, because these are just tree diagrams that you have to do, and you have to like add up all the outcomes and whatnot. But this takes a long time, and I don't think they would pull this on an exam. I know they never did for us. I think they just want you to understand the concept. So, I mean, if they were looking for 2 bases, right, we know that 2 bases is 2 slots. So if I have 4 outcomes in the first like base, I can either get ATGC. If I have 2 bases, that's 16 total outcomes, right? I'm looking for how many outcomes contain 1 or more T's, right? So this would have 1 T, this would have 2 T's, for example, right? So then I'd have to go through and be like, okay, well, here's an outcome that's favorable, right? Here's another one, here's another one, here's another one, right? Because they all have 1 or more T's. Here's another one, there's another one, right? I'd add all those up. I have 7 out of 16, for example, right? So, once again, this is just histograms. Yeah, I mean, we kind of went over these a bunch of times. Watch out for percentages here. So like 20 is not the probability. This is 20%, which is 0.2. So when you're multiplying your probabilities, when you figure out averages and whatnot, make sure to have 0.2 and not just 20. And then oftentimes when doing those problems, like the one that you saw on the written homework and the one on the quiz, they're gonna like be using the central value most of the time. So like this would be 50, 100 to 200 would be 150, for example, and so on and so forth. Those are like the X values that you would use, or the V values, or whatever, right? for your probability when you're when you're calculating your averages. And then yeah, this is just like the same base stuff again. I would go over those real quick. This is what I was talking about for probability of combined processes. So if I roll 2 coins, right? Well, probability, and I'm looking for the probability of getting heads on both. Well, I know the probability of getting heads on the first is 1/2. Probability of getting heads on the second is 1/2. So 1/2 times 1/2 will give me 1/4. That's the same for rolling the dice, right? So I can roll 2 ones. I know that the probability of rolling a 1 at all in the first roll is 1/6. Probability of rolling a 1 again in the second roll is 1/6, right? Because they're independent. So 1 out of 36 for rolling 2 ones, right? So that's the probability for combined processes. And then this is just the averages that we keep talking about over and over again. I feel like I've repeated this like a million times. The only thing that I'll go over again, I guess, just because I haven't mentioned it today, is the standard deviation. So just be watchful of this equation right here, because there's the average squared with the exponent on the inside and the average squared with the exponent on the outside, right? So just be careful of that distinction there and make sure you plug in the correct values for each and take the square root after subtracting them. And standard deviation is just an indication of like how much all the values in the distribution deviate from the mean or from the average, right? How wide the distribution is. So if there's large deviation, right, 15.8, the values are going to deviate a lot from the mean, so it's going to be more spread out, right? If there's low deviation, everything's going to be kind of close to each other, to the mean, to the average, right? So yeah, but that's the gist of what you guys need to know. I would go over some of these example problems or quick checks as well, just to kind of refresh your mind on some of these concepts, but that's pretty much it. I don't have anything else, to be honest. We went over the quiz problems, right? Highlighted some things to go over. But yeah, I would make sure you really know probability and really understand the average stuff, because that's most likely what they're going to be asking for. But yeah. One or more t's. Wait, what do you mean? Oh, like the quick checks? The ATGC one. Gotcha, okay. Which one do you want to go over? Just any random one? Because I could go over this one, for example. Like this one. Okay. Yeah, we can go over both if you'd like. So right here they're saying consider a sample space which consists of all possible combinations of 2 bases. Assume that the probability distribution over all combinations is uniform. So that just means that each outcome is the same probability. What is the probability that when a combination is chosen at random, that it contains 1 or more t's? So 1 or more t's just basically will mean like, well, if I have a t, that's 1 t, so that qualifies. Or a tt, that's 2 t, so that qualifies. tg, that's 1 t, that qualifies, and so on and so forth. So first of all, I'm going to look for how many total outcomes I have. So if I'm looking for 2 bases, right, well, I know that in each base, right, I have 2. Let's think about bases as like slots, right? So I have 2 slots. Each slot has 4 like outcomes. I could do A, T, G, or C, right? So in each base or each slot, right, or each like trial, I have 4 outcomes, and I have 2 bases or 2 repetitions or 2 trials or 2 bases, right? So that's 4 squared, which is 16 total outcomes, right? And now to figure out how many of those 16 total outcomes have 1 or more t's, then I can do kind of like a tree diagram. So I can just literally write out AA, AT, AG, AC, right? Those are the possible outcomes that I can have with A, right? AA, AT, AG, AC. I can also have TA, TT, TG, TC, right? Same for G, right? I could have, and this is, by the way, like, this is signifying, like, these are the possible outcomes for the first base, and then these are the possible outcomes for, like, second bases, right? So for my first base, I could have A. For my second, I could have A, I could have T, I could have G, I could have C. Same thing here. Like, for my first base, I could have T, for example, and then for my second, I could have A, T, G, C. My first base, I could have G, and then my second, I could have A, T, G, C, and so on and so forth. So you could just kind of like write down all the different combinations, and then we're looking for the ones that have one or more T's, right? So there's AT, that has one T, so there's 1 out of 16, right? There's TA, TT, TG, and TC. They all have one or more T's. So TA has one T, TT has two, TG has one, TC has one, right? So 4 out of 16 in that case, in this little section here, have one or more T's. This one here, only GT has one or more T's, which is 1 out of 16. CT is the only one here that has one or more T's, so that's 1 out of 16. So 1 out of 16, right? Plus 4 out of 16, plus 1 out of 16, plus 1 out of 16 will get you 7 out of 16. So these problems is really just about, like, first of all, figuring out your total outcomes, and then, like, really just looking for what condition they're looking for. So if they're asking for this next one, like, how many of them have exactly one A? So I'm just going to go back and look at which ones have exactly one A. Well, this is AA, so that doesn't qualify. But I have AT, AG, and AC. So that qualifies, right? So that's 3 out of 16, for example. This has 1A, that qualifies. This has 1A, that qualifies. This has 1A, that qualifies, right? So 3 out of 16 for this one, 1 out of 16, 1 out of 16, and 1 out of 16, right? So 3 out of 16, 1 out of 16, 1 out of 16, 1 out of 16. So that's 6 out of 16 for those that contain exactly 1A. So you would essentially just have to go about and kind of draw out the combinations. And the reason why I say I don't think this is going to pop up on a quiz or an exam is that it's just too lengthy. Now I don't want you to, like, just kind of overlook it and then have it come up on the quiz tomorrow and freak out. But I'm just saying, like, I personally don't think that they would pull it because you only have so much time, and if you have, like, one of those average questions, that's going to take up a large portion of your time, and they're just really just testing if you understand general probability or not. They're not here to, like, test if you can draw tree diagrams. So I would still make sure you know it, just that you understand what's going on. But hopefully that made sense for the bases. Thank you. You too. And I will make sure to upload this as soon as possible. Yep, no problem, guys. I will end the recording here.